All right, welcome everyone. Just going to get started here in 1 minute. I'm trying for the first time having live Q&A from the online audience. Okay, welcome to class 3, everyone. We're going to change gears a little bit today from your sort of basic introduction to data and numerical and graphical summaries of data into a bit of probability. We're going to cover it in the context of Bayes' rule. I'm sure you all have a little bit of probability yet, but we're going to bring it up in the context of screening tests. So tests that are imperfect but can be used to screen for disease in a population. And in this context, review some of the basic properties of probability and of conditional probability, and use those along with some notation that I'll introduce to teach you about Bayes' theorem and its application to screening tests. So something a bit different from the rest of the class, but it's an interesting, kind of a fun topic, I think, because it is quite relevant to a lot of things that we've all probably thought about and heard about. So let's start out with this example hypothetical test here. First of all, do we have anyone online? If you have something online, and you can hear me, please send me a chat just so that I know. I'll continue on here though, because I'm pretty sure it's working. So this is a hypothetical test. We have a screening test for cancer, and it is correctly positive in 100% of cancer patients, which is what I mean by which I mean if you have cancer and you take this test, it will identify that you have cancer. It will never incorrectly say, no, you don't have cancer, okay? So if you have cancer, it will detect it. That means very, very high sensitivity. So if you have cancer, it will detect it. Now let's say that we apply this to a population where the prevalence of cancer is 5 per 1,000. And if we apply it to this test, let's ask the other question. So we know that if you have cancer, there's a 100% probability that it will detect it. Conversely, if it detects that you have cancer, what is the probability that you have cancer if you're a member of this population who has received the test? Great, and thanks everyone online. I see your chats. And please feel free to chime in and answer the question. Who thinks they know the answer here? So you've received a positive test. How worried are you of this hypothetical test? It's not a real test.
Very worried.
Very worried. Very worried because what?
It's correctly positive 100% of the time.
Just to be sure I'm clear here, it's correctly positive for 100% of cancer patients.
Oh, so it might also be correctly positively identified non-cancer.
That's right. I didn't say anything about how it performs on people without cancer. That's an important point to make there. So it's 100% correct on cancer patients, but I haven't told you how it performs on healthy people.
How we don't know about the specificity of the test, right?
You don't know about the specificity of the test. That's right.
Might test positive in non-cancer patients.
Yeah, you might test positive even if you're not a cancer patient, or even if you're not, you don't have cancer anywhere in your body. So you're, I think, on the right track here. So anyone else want to tell me how worried should you be?
It should be 100% sensitive and 100% specific.
Oh, it should be. That would be great. But I haven't said that it's both of those things. That would be a perfect test. Not many tests are perfect that way. And I'm not saying this is a perfect test. I'm just saying that it's perfect on cancer patients. So it's 100% sensitive. Yeah.
Would it just be 5 over 1,000? Because I mean, who's ever getting tested, who's ever has cancer, is testing positive. So I don't know really explaining it, but
yeah. So 5 out of 1,000. What were you saying is 5 out of 1,000?
That would be the probability, because
the probability of what?
The probability that you would have of the individual in this population who tested of having cancer.
So that's interesting. You're saying that if you tested positive by this test, you would figure that you have a 5 in 1,000 chance of having cancer, the same as you had before you took the test.
No, that's not exactly what I'm trying to say.
I'll just say that that's possible because I didn't say anything about how it performs on the rest of those people without cancer. Yeah?
Yeah. If the individual with 1,000 population, general population is 1,000.
Yeah.
And 5, if it is test positive for 10 people.
Test positive for 10 people. By the way, you folks online, I see your comment, positive predictive value. Are you able to hear the questions from the room? Because supposedly these hanging mics should be on, and you should be able to hear. You should be able to hear other people as well. So sorry, go ahead. What was your comment?
I'm going to say if it is positive for and if 10 people is positive with the test, then it might be possible that out of 5 people are true positive.
Right. So that's one possibility. Maybe in this population, 10 out of 1,000 test positive, and since we know it catches those 5 that are positive, then if you test positive, you have a 50% chance. So you've gone from having a 5 in 1,000 chance to having a 50% chance. Yeah, but the important thing is that it entirely depends on its performance in those 995 healthy people. And I didn't tell you that, so we have no idea. Great, the voices are all clear to you. That's wonderful. I've never had this working before where you can hear not only me, but the people in but the students. So we can't answer this question because I told you about the great performance on those 5 out of 1,000, but nothing about the performance on the other 995 out of 1,000. So let's take let's say this is a trivial test where the test is just a piece of paper that says you have cancer and they hand it to everyone. Then that still meets this requirement. It's correctly positive for 100% of cancer patients, but it's not a good test because it's not specific. So it depends on both of these things. What that question of what is your probability of having cancer given a positive test, which is the positive predictive value, as Krishna pointed out for us online. So ideally, the test would be 100% accurate. As you suggested, maybe this one was. It would have 100% sensitivity and 100% specificity, in which case we wouldn't have to worry about anything we're covering today. You would just take the answer, and that's the answer. But this is not the way screening tests work. In reality, they have false positives. They have false negatives. So, so that's bad enough. But the performance of the test depends on not only properties intrinsic to the test, but it depends on the population that it is applied to. So the same test applied to a population with very low prevalence of the disease will have a different performance in terms of these things we care about, like positive predictive value. If given a positive test, what is your probability that you really have the disease? It'll perform differently for that in a low prevalence population than in a high prevalence population.
Why is that? That the test will perform differently depending on the prevalence of the disease?
Because, so it performs differently depending on the prevalence of the disease, because it has different performances on the cases and on the healthies. So on the cases with disease and the healthy individuals. So depending on that proportion of them, its performance on those two groups, those with and without the disease, will have different relative importance. The more and more healthy people you have, the more important that performance on the healthy people is, that specificity, the ability to say you don't have the disease. So in very, very low prevalence population, that specificity, that performance on healthy people is extremely important. Whereas if you have a high prevalence disease, then that sensitivity, that ability to detect the disease in people who have it becomes more important. So we're going to learn methods today, how to take the properties that are intrinsic to the test, apply them to the population, and get answers as to the things that matter to the patient and the doctor, which is, you have a positive or a negative test, what does that mean to you? Which is a property not only of the test, but of the population in which you live. And by the way, we will be using what we call a gold standard, which is some expensive test that can be used to follow up and is highly accurate. So it's something that it would not be feasible to apply to as large of a population, but can be used to confirm the truth. So, you know, if step one is some screening test for cancer, step two would be a biopsy and a pathologist studying your specimen under a slide to make a positive or a definitively positive or negative conclusion about whether you have cancer. Yes?
So when you use like the word performance, it seems to have like a very specific connotation of like sensitivity together with specificity, right? I mean, would you say that's like a fair thing to say, that performance is basically equal to like, you know, some kind of sum or whatever of the specificity?
Yeah. So we'll talk a little bit more about performance. There are many different ways to define the performance of a test, but in general, the performance of a test depends both. It depends on how well it can discriminate between the people with disease and without disease, and yeah, we'll talk about that a little bit more. But it depends on all of these things: properties of the test, where we set the threshold, the population that it is applied to. Right. One more example. This one a little bit more realistic, just to give you a better idea of what we're talking about. So we have a PCR test, polymerase chain reaction, to identify chlamydia, and it is being applied in two different clinics. One is a sexually transmitted disease clinic, and the other one a private practice, with the difference being that in the STI clinic or STD clinic, there's a higher prevalence because you have more people going there specifically because they have noticed some symptoms. So this is the same test being applied to the patients in two different clinics. So let's see my mouse here. So properties, and here we have the data. We have positive and negative in the columns. These are from our gold standard. So this is some follow-up where it was determined absolutely whether these individuals have chlamydia or not, and then the results from our screening test. So if you look at this clinic, it's about one third, exactly one third, 300 out of 1,000 are positive and 700 out of 1,000 are negative. And it's only 1/10 the prevalence in this other population. So our sensitivity is, hi Tony. The sensitivity is the proportion of the positive cases who are identified. So to determine sensitivity, you would look only in the positive column, and you would find that 294 out of 300 of them are identified. So it's very high sensitivity. And that sensitivity is the same in both clinics because it's a property of the test. So 29 out of 30, I mean, there's a little bit of rounding error here. It's a limited sample. And the specificity is the performance on the negative cases. So we look only in the negative column and see the specificity is 679 out of 1,000 here, or 941 out of 970. And that should be about the same in both clinics. But the positive predictive value is different. So the positive predictive value, we're looking at rows. We're looking at the people who tested positive. How many of them are actually positive? So it's 294 out of 315 in the STI clinic and 29 out of 58 in the private practice. So this positive predictive value is 93% in one clinic and only 50% in the other clinic. So in terms of this one metric that is of great importance to the patient and the doctor, we're seeing very different performance in these two populations just because of the difference in prevalence. Any questions so far?
So just quickly, specificity, that's neither the positive or negative predictive value.
Right. Right. Specificity is the performance on people who do not have the disease. So performance is if you look at people who do not have the disease, it's the accuracy there. It's correct in 679 out of 700 healthy individuals. So the reason that sensitivity and specificity don't depend on the population is because the prevalence doesn't matter. You're looking separately at the people with the disease and without the disease. It doesn't matter what the prevalence is in the population. Whereas with PPV and NPV, you're looking at the people who tested positive and who tested negative. So it does matter what the prevalence is in the population. Now we've got our examples. Let me give you some definitions. An event, this is a measurable outcome. So this is whether or not the individual has chlamydia, has cancer, survives past a certain age. This is, and this is not just in screening tests. An event is an important concept in probability. It's something, it is an outcome. It's something that either happens or it does not. It's something that you observe and it has a real value. Whereas the probability is something that is a little bit less concrete than that. If you observe an event, you don't know what the probability of it is. In order to actually observe the probability, you would have to observe many, many of those events and look at the frequency with which each of the possible outcomes of that event occur. So if you look at 1 million people and 700,000 of them test positive for something, then the probability of that outcome is 70%. But you have to make many observations. Well, you don't have to make 1 million. The more you make, the more accurate your estimate could be, but it's something that you only observe or that you can only estimate from repeated observations. There are other ways we could think about intrinsic properties of the test, but these are the ones that we're going to focus on, and really the most commonly used ones. Sensitivity, which is the probability of an individual who has the disease testing positive, so you're only looking at the people who have the disease. And specificity, conversely, is the performance on people who do not have the disease, so the probability of a negative test given that you do not have the disease. So does everyone understand why I'm calling these intrinsic properties of a test? Is anyone unsure?
Sure.
Yeah.
So they're intrinsic because
because it is the performance. It is the performance of the test on individuals with the disease and without the disease. So it is on people where it is known from the gold standard whether or not they have the disease. And so I'm calling these intrinsic properties of a test because it does not depend on the population to which it is applied. The properties, unlike positive predictive value and negative predictive values, which are properties of the test applied to the population. So let's get a little bit more visual with these, with another example of type 2 diabetes mellitus. So this is a disease that has high prevalence in certain populations, especially elderly obese populations, and much lower prevalence in other populations. There is a gold standard, which requires fasting and drinking a glucose solution and then drawing blood at intervals for measurements of the glucose to see how much of it is being processed or how much is going straight into your blood. Difficult, invasive test that involves multiple blood draws, not something that could be used for screening. The screening test is fasting plasma glucose, so you don't know if, in this case, how much sugar or what the person's normal level of glucose is. You don't know how it's being affected by them just sort of in their background. You just have them fast, you take a single test, and based on the glucose measurement, it gives some idea of whether they are more or less probable to have type 2 diabetes. So it's fast, convenient, and less expensive than the full diagnosis, but less accurate. So perfect example of what we're talking about today. So let's take this screening test and apply it to 20 diabetics and 20 non-diabetics and make up some fictional data as to what the result is. So what I'm showing here are the two groups, the diabetics and the non-diabetics, and we know who they are from the gold standard test. And we've measured blood sugar in both of them. And the key thing you see here is that there's a lot of overlap between them. This is why it's not a perfect test. So in general, diabetics will have higher fasting glucose than the non-diabetics, but there's a lot of natural variation, and based on this test, without the intervention of having the person take glucose and then taking regular blood draws to see the response to that glucose, this is the best you can do. So the key thing is that our measurement here is continuous. It's not just giving us a yes, no, you have diabetes or you don't. That depends on a threshold that you set. So, and you could set your threshold anywhere in here, depending on what your objectives are. You could set a low threshold. So, you know, if you have almost any blood glucose at all, and you're above that threshold, you get called diabetic. Okay, so you're going to call a lot of people diabetics, but you're also going to call a lot of non-diabetics diabetics. So what would you say about this test in terms of sensitivity and specificity? Is that going to be good sensitivity, bad sensitivity? Good sensitivity, yeah. How about specificity, good or bad? Bad, right. So the sensitivity is the performance among the diabetics. You see it's pretty good. It catches most of them. The specificity is the performance among the non-diabetics. It's pretty bad. It called most of them diabetics anyways. So setting the threshold low gives you a high sensitivity, 85%, and a low specificity, only 30%. So it got 85% of the diabetics right and only 30% of the non-diabetics right. Yes?
By setting a no threshold, does that mean that it applies to any types of tests? Once you do that, then sensitivity is going to be much higher than specificity?
By doing what?
Okay, does this apply to every single test, or it's just unique to this example? Once you set the threshold so low,
this is a general, yeah, this is general to any test where you're measuring something continuous, and then you have to set a threshold to determine where it's going to be a positive test. So, you know, that's not all tests. Some tests are just, you know, a yes or a no. They're not on a continuous scale. In fact, PCR tests are usually just yes or no. But this, where we're measuring blood sugar in like micrograms per milliliter, is continuous. So you have to make a decision about where to set the threshold to call that a positive test. And the lesson to be had here is that there are trade-offs. And where that trade-off is made is going to depend on the relative importance of this kind of mistake and this kind of mistake. The false negative and the false positive. Yes?
Just theoretically, so if you move the threshold all the way up, let's say, to like almost the top, like to like between blood sugar, like between the label for blood sugar and the label for high.
Mm-hmm.
So then, let's say there would be like 2 non-diabetics, like above the threshold, and 5 diabetics. 2 non-diabetics above the threshold and 5 diabetics above the threshold. Then the test would be, you'd be reducing the sensitivity, and you wouldn't really be improving the specificity all that much. This is just like totally theoretical, just here.
Oh,
if you moved up, let's say you decided to move your cut point up.
Yep. Like this.
Yeah, exactly.
Yep.
Yeah.
Yep.
Okay, so that's the next thing. Then okay.
Yeah. So yeah, if we move the cut point up, then we see we're performing worse on the diabetics and better on the non-diabetics. So we've improved we've made our sensitivity worse, and we've made our specificity better. And it's a trade-off. That is a very general thing, that there's a trade-off between sensitivity and specificity. Unless you somehow improve the test itself or find a different test, there's only going to be a trade-off between these two. If you make one better, you'll make the other worse.
It would be always like that, like one is good and one is bad?
Almost always. I mean, if you get to a point where there is some non-overlap in these two distributions, you might be able to improve one while keeping the other one constant. You'll never be able to improve both at the same time without getting a different test.
So what's the standard then on epidemiology when you're testing, like, you want to test like the product to see if it's work or not?
Yeah,
Do
what
you work at sensitivity or the specificity?
it's a good question. Do you care about sensitivity or specificity? And I don't think I can give a general answer about that. And I don't even know all of the things that go into a decision like that, because it really does depend on the clinical options and on what the relative costs of those false positives and false negatives are. And it's a source of controversy, as I'll point out, because they do both have costs, and different people have different ideas about what those costs are. I mean, if you have cancer, the general thinking is that the cost of a false negative is very, very high. If you have cancer and it's not detected and it spreads, you can die from it. So the cost of a false negative is very high, and there has been a tendency to really err on the side of false positives. But there are problems with that as well. As you start identifying a lot of false positives, there can be adverse health impacts of that as well, which can end up outweighing the benefits of avoiding the false negatives. Yes, it's a cutoff. Thanks, Krishna. It is the cutoff point or a criterion. To me, it's a cutoff point or a threshold. Could be called a criterion as well. So keep in mind, though, this would be a testing phase where we have the gold standard truth for everyone. But in real life, or when we go and apply this in a clinic where we don't already have the gold standard result for everyone, the two groups are mixed. We don't know who the diabetics and the non-diabetics are, and they're not labeled. So all we have is a bunch of people coming into the clinic, and we apply the test, we apply the threshold or the cutoff, and we know who we call diabetics and who we call non-diabetics. And if we know some things about the properties of the test and about our population, we can calculate what this means to these people who received a positive test and to those who received a negative test. And here's something to think about. If you receive a test like this, you can probably get some kind of advice from your doctor about what this means, how accurate the test is. But you should know that that does depend on the prevalence of whatever the condition is among people like you, whatever that means in the context of the condition you're being tested for. So the high threshold, all we know is that we identified 7 people. The low threshold identifies 31 people. We know that there would be different sensitivities, specificities, PPV, NPV for those different decisions. I think we've covered all of these points already, but they're there in your notes for you. Just a summary that the threshold or cut point determines the sensitivity and the specificity of the test, as long as there is some difference in the distributions of the measurements between those with and without the disease. So whereas sensitivity and specificity are what I call intrinsic properties of the test, PPV, positive predictive value, and negative predictive values are properties of the test when applied to a certain population with a certain prevalence of the disease. And these are the things that actually matter to the patient. So the positive predictive value is the probability that someone with a positive test has the disease. Negative predictive value is the probability that someone with a negative test, in fact, does not have the disease. So back in this example, the sensitivity and specificity were in the columns here, the performance on the diabetics and the non-diabetics, whereas the PPV is the performance on those with a positive test, and the NPV is the performance on those who received the negative test. So it's the probability of being correct for those who got a positive test and probability of correctness for those with a negative test. Now, this has been a source of debate in a few different diseases. Prostate cancer, breast cancer being big ones. Because you can imagine that even a pretty good screening test, and maybe one like prostate cancer that has performed pretty well in high-risk populations, it becomes tempting to expand that testing to younger and younger people, people at lower and lower risk. And at that point, that specificity, that performance on all of those negative cases becomes very, very important. So if you receive that positive test, your probability of having the disease, it depends on what we call your prior probability of having the disease. So before you walked into the clinic, what was the probability? If you are a 30-year-old with no history of cancer in your family, your prior probability is very low, and your probability after receiving a positive test is probably still fairly low. Whereas if you're elderly with a history of cancer in your family, you have a higher probability stepping into the clinic, and your probability after receiving a positive test of having cancer will be even higher. And we can calculate those relationships, but you need to know a bit of probability notation. So remember, events, these are observable things with an observable outcome, such as having cancer. And if A and B are two different ones, the key notation I want you to know are the union, looks like a U, the intersection, the upside down U. The complement, which is not A, so if A is having cancer, then A complement is not having cancer. With the sum of these two always being 1, because you have to either the event has to occur or not occur, even if it's something where there are many alternatives, such as like rolling a dice, where if A is rolling a 1, then A complement would be rolling a 2 through 6. So it is everything else besides this one event that might happen. And one more that's really important for what we're covering today, the conditional probability, which is notated by a little vertical sign like this, sometimes called a pipe, but it's used for conditional probability. So it's the probability of A conditional on B already having happened. So the probability of A conditional on B, it means you assume that B has already happened and then ask what is the probability of A, conditional probability. It's nice to represent these as Venn diagrams where each event is a circle, and the area inside the circle represents a probability, and then an intersection can be represented as the overlap between these circles, And you can do this for 2 events, 3 events. You can draw Venn diagrams for up to quite a few events. But here in the middle, you see that this probability is A intersection with B intersection with C. All right, a couple little interactive questions for you. Please join in online too. How would you write down this probability shown in the Venn diagram in number 1?
AC.
What's that? In number 1?
Yeah.
Doesn't look to me like it depends on A at all.
Oh, it's a B.
It's just probability of B. Yeah. Yeah. I wonder if I can write on this. And let's see if I can. Probability. I forgot to bring my my writing tablet. So that's probability of B. Very good, online folks. You got it. Probability of B.
What about the area in between though, A and B?
Well, what about that area in between?
So that's not considered to be A intersection B. If the rest of that isn't highlighted.
Well, it's a good point. So there are actually other ways that this could be written. Probability of B is the simplest way to write it. But another way we could think about it would be, let's see, this part in the, where's my cursor? So this part here, actually that's a question down here. This is the probability of B intersection with a complement, right? So it has to be in B and it has to not be in A. And this one here, number 6, what can we call this? What's that? Yeah, A intersection B. So this kind of gives a clue as to another much more complicated way we could have given the answer to 1, right? Because it's kind of the sum of these bottom 2. It's like the union of those 2. So we could have written the answer to 1 as the probability of B intersected with A complement and then intersected with the probability of A intersect B, if you wanted to be complicated about it. But it also happens to just be the probability of B. Okay, quickly, number 2. I like how online I can see that the B closed bracket turns into someone with sunglasses. Google Chat, the emoticons are not built around probabilities. Oh, so, okay, sorry. So what is something for? Yeah, I see a right answer online. What is number 2? A union B. Yep. Number 3. Yep, just A. And number 4. Well, just a sec. I heard a lot of different things. It's getting more complicated now. What was yours?
I was saying actually wrong. It will not be in union. It will be intersection.
Yeah.
Probability of A intersection B complement.
Yes, A intersect with B complement. Maybe I'll spare you writing it out here because I'll write it out. Probability of A intersection with B complement. All right, you guys are probability pros.
Why wouldn't 4 just be B complement? Probability of B complement?
Well, okay, so why wouldn't it be just B complement? That would also include all this stuff out here. Like B complement is everywhere outside of B.
Okay.
But here it has to be outside of B and it has to be inside of A. So it's the intersection of A with B complement.
So we're like looking at these two events inside just like a greater scheme of other events. Imagining that there's like a C and D and E, like all.
No, just these two events, but you know, with A, one outcome is that A occurs, and the other one is that it doesn't occur. So whatever it is, we don't have to have. So let's say here, these are two events. Each of them has one outcome that's represented by the Venn diagram, and then everything else. So this could be, say, A is having cancer, B is having diabetes. Then this would be the probability of having cancer but not diabetes. Mm-hmm.
So why is 2? So 2 is A union B as opposed to A intersection B, because it's, if it was A intersection B, it would just be the overlapped areas.
That's right. This is number 6 is A intersection B, and number 2 is A union B.
Okay, so it's only the parts of A and B that overlap.
Yeah. So A is, you know, having either cancer or diabetes, and 6 is being very unlucky and having both. All right, so if we have, if these two events are mutually exclusive, such as having chlamydia or not having chlamydia, then there's no overlap in the Venn diagrams. And we can write that out by saying that the union of the two is just the sum of those two probabilities, because there's no overlap. If there was overlap, would that union, this probability of the first event union with the second, would it be more or less than in this case?
What's the question?
So the question is, this is the probability of the union for mutually exclusive events. If they're not mutually exclusive, would it be more or less than this?
If they weren't exclusive events,
Yeah, if they're not exclusive.
it would be more likely, right, that you could have, it's impossible, there's a 0 probability of having C positive and C negative, right? That's if they're mutually exclusive. So the probability is 0. If the two events can occur together, the probability is by definition more than 0, right?
I'm not sure I'm following, but let me explain a little bit more. So the probability of the union of these two events, so this would be the probability of either having chlamydia or not having chlamydia, is just the sum of those two events. If they were not mutually exclusive, there would be overlap here, and that probability would be less than what we write here because of that overlap. You wouldn't just add them because there's also a probability that you have both. In this case, because the options are exhaustive, that union has to add up to 1. So there's only 2 outcomes, and it adds up to 1. If this were 1s and 2s on a dice, then they would still be mutually exclusive but not exhaustive. And because they're exclusive, the probability of the intersection is 0. Now, as soon as they're not exclusive, such as, say, having chlamydia or having heart disease, then we have this overlap. Okay, so there's some intersection of these two non-exclusive events. And as I mentioned, remember before we just added these two probabilities, if you just do that, you're counting this intersection twice, so you actually have to subtract it to correctly calculate the probability of this union. So your probability of having chlamydia and heart disease is your probability of each of them individually minus the probability of having both, so that you're not counting those cases that have both twice. Kind of make sense? And this is an important rule. You can also write out the intersection as the product of these two probabilities if they are independent. So if having chlamydia and having heart disease are completely independent, having one does not increase your probability or decrease your probability of having the other, then the intersection of the two events, the probability of that is the product of the two individual probabilities. So the conditional probability, which I mentioned, is the probability of one event occurring conditional on the second one already having occurred. So this is the probability of A conditional on B, and it's equal to the intersection of 2 divided by the probability of event B having occurred. So let's put this in some, I don't know, concrete example. If you're flipping a coin, your probability of having 2 heads in a row is 1 out of 4, but your probability of getting 2 heads conditional on the first flip already having been heads, you have to divide by the probability of that first event, and you get a half instead of a quarter. Or back in that example of heart disease and chlamydia, your probability of having heart disease, given that you have chlamydia, would be, obviously you have to have both of them, but since it's conditional on having chlamydia, you have to correct for the probability of that having happened. And here it's just written out in terms of the Venn diagrams. It's the intersection divided by the probability of the event that is on the right-hand side of the conditional sign. Yes?
Good question. When you write probability of A and B, is the same as probability of A intersecting B?
Yes.
There's exactly
same thing. Okay. Means exactly the same thing. This is the probability of both events occurring. Yeah, I use and intersection interchangeably, just as I use union and or interchangeably. They mean the same thing. And this is going to bring us to Bayes' rule. And it's actually, given that equation on the previous page, it's a very simple derivation. It's just a basic rule of probability. And it comes from that rule and this observation that the intersection is commutative, that the probability of A and B is the same as the probability of B and A. The order there doesn't matter. Then we use that equation we had on the previous page just to expand this out, written in these two ways, as conditional probabilities, and then just divide through by this probability of B, and we have here Bayes' rule. And each of these terms has their own terminology in Bayesian language, where this probability, this conditional probability on the left-hand side is the so-called posterior probability. This probability of A is the prior probability. The next term there is the likelihood, and that denominator is just like a normalizing factor. And this is very important for our calculations on screening tests and for interpretation. So when I was mentioning that if you go in for a prostate cancer screening test, what this is telling you, so this is, let's think of A as having prostate cancer and B being a positive test for the screening test. So then I would read this as your probability of having cancer given a positive screening test is equal to your probability of having cancer, your prior probability of having prostate cancer, that's the prevalence, the prior probability, times the probability of a positive test given that you have cancer. That is, we learned about that before. What's that called? Your probability of a positive test given that you have the disease. No, that's the sensitivity. Yeah, that's the sensitivity. So it's the prevalence, your prior probability, times the sensitivity divided by the probability of the prior probability of a positive test. So, and those will allow us to calculate the positive predictive value. So is the probability of A conditional on B equal the probability of B conditional on A? No. Good. You're absolutely right. No, it doesn't. Only when the prior probabilities of those two things are the same. For example, the probability that you would retire given that you had as much money as Trump, is that the same thing as the probability you would have as much money as Trump given that you've retired? No. They're just different things. They would only be equal if the probability of you retiring is equal to the probability of you having as much money as Trump, which doesn't make any sense. Okay, so I think I'm going to skip over this because we're getting a little bit short on time, and I do have another example here. The key thing about what we've done here is that it allows you to take these intrinsic properties of a test, the sensitivity, the specificity, use those as that's the likelihood in Bayes' rule and the prevalence of a disease in the population, and calculate these posterior probabilities of having the disease or not having the disease, the NPV and the PPV. So given the prevalence, a property of the population, the sensitivity and specificity properties of the test, we can then apply these to a population with a given prevalence and calculate the PPV and the NPV. And I can ask you to apply this to any different population with different prevalence of the disease and recalculate the PPV and the NPV. And you will know that, that if you're told something that sounds like a PPV, there's an assumption in there about the prevalence of the disease in the population from which you come. So let's, I'll let you calculate these on your own, but they will, and I think you'll be doing a few more of them in lab session today. But these are some very explicit examples on calculating them.
What does the T stand for?
So here the T is a positive test. So this is the probability, PPV is the probability of having chlamydia given a positive test, which is equal to the probability of having the prior probability of having chlamydia, which is the prevalence, the probability of a positive test given that you have chlamydia, the sensitivity divided by the probability of a positive test. And that, of course, that prior probability of a positive test depends on the population as well. It's fine with me if you use a calculator. There are online tools for calculating Bayes' theorem. I also put an Excel spreadsheet, Bayes' rule calculator with the lecture notes, which, and you'll be welcome to use that for your exam as well as for the assignments. What I really care about is that you have some intuitive understanding about how it works, so that things will not surprise you, such as, so here is our example from the STI clinic with the high prevalence, 30%, the high sensitivity, and the high specificity, the 93% PPV. Then we go and apply that to a lower prevalence population, see the PPV go way down. And even if we increase the sensitivity to 100%, it has hardly any effect on the PPV, because it's still not performing any better on that majority of negatives. So you know now about conditional probability, and you know that the conditional probability of A given B is not the same as the probability of B given A. And you know that you can use Bayes' rule to go back and forth between them, but you're going to have to know the prevalence or the prior probability, and you're going to have to know that probability of a positive or negative test in the population. And you'll remember that sensitivity and specificity, these are properties of the test. It's how accurate it is on people with the disease and how accurate it is on people without the disease. And you'll know that PPV and NPV, these are properties of the test when applied to the population. And it also depends on the disease prevalence in that population. Take those and your bit of new notation you have and the ability to calculate some of the basic probability calculations that we covered, and you'll be in pretty good shape from today's class. Are there any more questions before we take a 10-minute break and then start up at 6:15 again? All right, thanks everyone who attended online. Oops.
Relax. If you understood this the first time you've seen it, there's something wrong with it. Okay, so relax if it seems confusing. Takes a couple of times to kind of let this stuff sink in. There used to be a game